Option 4. A parallel arrangement of unequal capacitors. Consider a parallel arrangement of an 8 microfarad and a 12 microfarad capacitor. This relationship yields a total capacitance of 20 microfarads. Despite the unequal capacitance values, all parallel properties remain true. Notably, voltage across elements in parallel is the same, and total current through the parallel arrangement is the summation of current through the individual capacitors comprising the parallel arrangement. I total equals I1 plus I2. Unlike our previous analyses featuring identical capacitors, current will now be apportioned differently between these different capacitors. Allow me to demonstrate. To explore this phenomenon, let's say the parallel arrangement is hooked up to not a Thevenin's equivalent circuit, but rather to a 10 microamp current source that continuously pumps a small amount of 10 microamperes of current into this parallel relationship. Let's say we do this continuously for a time span of 12 seconds. Note this current source steadily and continuously supplies a constant amount of current. Given constant current, voltage across this parallel combination of capacitors would steadily rise as more and more charges steadily accumulate. Again, we'll do this for a span of 12 seconds. Given a continuous charge transfer of 10 microamps, or 10 microcoulombs per second, for a period of 12 seconds, we've ultimately transferred 10 microamps times 12 seconds, or 120 microcoulombs of charge into our parallel arrangement. Given capacitance equals charge over voltage, an algebraic rearrangement of this expression suggests that voltage equals charge over capacitance. Substituting at our given values of total capacitance and charge yields a voltage of 6 volts. Given these two capacitors are in parallel with one another, this means V1 equals 6 volts, as does V2. Voltage across elements in parallel is the same. My question to you is this: how did V1 get to be 6 volts and V2 get to be 6 volts if they have different capacitances? The answer is rather simple. These two different capacitors store different amounts of charge. Allow me to demonstrate. Given capacitance equals charge divided by voltage, an algebraic rearrangement of this expression also suggests that charge equals capacitance times voltage. Substituting at our given values for C1 at 8 microfarads and V1 at 6 volts yields a charge of 48 microcoulombs. Substituting our given values of C2 at 12 microfarads and V2 at 6 volts yields a charge of 72 microcoulombs. Note 48 plus 72 yields our total charge of 120 microcoulombs. For parallel relationships of capacitors, total charge equals the summation of individual charges. In this case, Q total equals Q1 plus Q2. These different capacitors hold different charges at the same voltage. It makes sense. Capacitance is a measure of charge storage ability at a given voltage. Capacitance is charge per unit volt. At the same voltage, the smaller capacitor holds less charge and the larger capacitor holds more. My follow-on question to you is this: how did these two capacitors attain a different charge over the same time span? The answer is also rather simple. These two different capacitors experience different rates of charge transfer, i.e. current during the charge process. Allow me to demonstrate. C1 accumulated 48 microcoulombs of charge over a 12-second period, meaning it on average experienced 48 microcoulombs over 12 seconds, or 4 microcoulombs per second, or 4 microamps of current. C2, in contrast, accumulated 72 microcoulombs of charge over the same 12-second period, meaning it on average experienced 72 microcoulombs over 12 seconds, or 6 microcoulombs per second, or 6 microamperes of current. At any point in time, 10 microamps of current comes into the parallel arrangement, of which 4 microamps goes into C1 and the remaining 6 microamps goes into C2. Kirchhoff's current law holds true at all times. I total equals I1 plus I2. Can you dig it? It takes a larger amount of charges in the larger capacitor to yield the same voltage. Thus, the larger capacitor in a parallel arrangement of unequal capacitors will always draw the largest amount of current. Conversely, it takes a smaller amount of charges in the smaller capacitor to yield the same voltage. Thus, the smaller capacitor in a parallel arrangement of unequal capacitors will always draw the smallest amount of current. This direct relationship of current and capacitance for unequal arrangements of parallel capacitors can be expressed as a proportionality as follows. Current through the capacitor of interest, Ix, is the capacitor of interest, Cx, divided by the summation of capacitors forming the parallel relationship. In this case, C1 plus C2 times the incoming current. In this case, 10 microamperes. Let's use this formula to directly solve for current through the known capacitors without having to calculate individual and total charges as previously. Substituting our given values for C1 and C2 in total current, we arrive at 4 microamperes for I1. The application of Kirchhoff's current law demonstrates that I2 is the remaining 10 minus 4, or 6 microamperes. This relationship works for this simple circuit employing a constant current source, as well as our original more complicated transient analysis of the charge process. Consider our original circuit at t equals 0, where we know incoming current for the total capacitance to be 150 milliamperes. An application of the direct proportionality relationship demonstrates that C1, the smaller capacitor, will draw 60 milliamperes of current, and C2, the larger capacitor, will draw the remaining 90 milliamperes of current. Regardless of the unequal distribution of current, voltage across the parallel combination of initially uncharged capacitors is 0 volts. Consider an occasion at 1.5 milliseconds, where we know incoming current for the total capacitance to be 73.6 milliamperes. An application of the direct proportionality relationship demonstrates that C1, the smaller capacitor, will draw 29.4 milliamperes of current, and C2, the larger capacitor, will draw the remaining 44.2 milliamperes of current. Regardless of the unequal distribution of current, voltage across the parallel combination of capacitors is 8 volts. Consider an occasion at t equals roughly 3 milliseconds, where we know incoming current for the total capacitance to be 36 milliamperes. An application of the direct proportionality relationship demonstrates that C1, the smaller capacitor, will draw 14.4 milliamperes of current, and C2, the larger capacitor, will draw the remaining 21.6 milliamperes of current. Regardless of the unequal distribution of current, voltage across the parallel combination of capacitors is 12 volts. Finally, at t equals 10.5 milliseconds, the charging process is complete and current flow ceases. Neither capacitor in the parallel relationship draws any current, and voltage across the parallel combination of capacitors is 15.8 volts. For this parallel combination of unequal capacitors, you can express voltage across C1 as V1 of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds. Voltage across C2 is V2 of t equals 15.8 volts times 1 minus e to the negative t over 2.1 milliseconds. Current through C1 is I1 of t equals 60 milliamperes times e to the negative t over 2.1 milliseconds, and current through C2 is I2 of t equals 90 milliamperes times e to the negative t over 2.1 milliseconds. At any time, voltage across these unequal parallel elements is the same. However, total current divides unequally. Moving on, let's examine option 5, that of unequal capacitors in series. This is perhaps the most counterintuitive of our 5 possible scenarios. However, a simplified circuit can be used to explore the situation with relative ease. As previously, let's make use of a 10 microamp current source, this time providing current to a series relationship of a 30 microfarad and a 60 microfarad capacitor. This series relationship yields a total capacitance of 20 microfarads. Despite the unequal capacitances, all series properties remain true. Notably, current through elements in series is the same, and total voltage across the series arrangement is the summation of voltages across the individual capacitors comprising the series arrangement. V total equals V1 plus V2. Unlike our previous analyses featuring identical capacitors in series, this time voltage will be apportioned unequally among these different capacitors. Allow me to demonstrate. To explore this phenomenon, let's say the 10 microamp current source continuously pumps a small amount of 10 microamperes of current into this series relationship for a time span of 12 seconds. Note this current source steadily and continuously supplies a small amount of current, or charges, per unit time. Given constant current, voltage across this series combination of capacitors would steadily rise as more and more charges steadily accumulate. As previously, we're going to do this for a span of 12 seconds. Given a continuous charge transfer of 10 microamps, or 10 microcoulombs per second for a period of 12 seconds, we've ultimately transferred 10 microamps times 12 seconds, or 120 microcoulombs of charge into our series arrangement. An algebraic rearrangement of the capacitance formula suggests voltage equals charge over capacitance. Substituting our given values of 120 microcoulombs and 20 microfarads yields a voltage across this series configuration of 6 volts. This total voltage will be unequally apportioned among the series combination of different capacitors. Let's examine the individual capacitors inside the series relationship. Given C1 and C2 are in series with one another, this means I1 equals 10 microamps, as does I2. Note that both series capacitors have been exposed to the same amount of charge transfer, i.e. current, for the same amount of time. As such, either capacitor will have a charge of 10 microamps or 10 microcoulombs per second for a period of 12 seconds, or 120 microcoulombs of charge. This seems odd. Total charge is 120 microcoulombs, as is the charge delivered to C1 and the charge delivered to C2. In fact, this whole arrangement, at whatever angle you wish to look, has a total charge of 120 microcoulombs. This seems like total nonsense, because if each capacitor has 120 microcoulombs of charge, it would seem natural that the whole system has 120 microcoulombs plus 120 microcoulombs, but that is most assuredly not the case. This is perhaps the weirdest behavior for series capacitors. The charge on each capacitor is identical, and the whole system has the same amount of charge. Charge total equals charge 1, which equals charge 2. The reason this system is considered to have 120 microcoulombs of total charge is found in the qualifier usable charge. Recall that current doesn't flow through capacitors in the traditional sense, but rather current into and out of a capacitor can be thought of in terms of displacement current, where a suitable analogy for displacement current can be thought of as a quantity of billiard balls on a table. When a cue ball makes a break on a billiards table, it strikes a ball, which in turn strikes another ball, which in turn strikes another ball, and so on, until eventually a ball falls in a pocket. While the cue ball itself didn't fall in the pocket, a ball went in and a ball went out. Think of this series relationship as two billiards tables, each with 120 microcoulombs of balls available to knock each other around. If you ever ran out of balls or room for balls on one table, the whole system ceases to function. One ball must knock another ball off the table onto the second table, which in turn knocks another ball off the second table, and so on. In summary, you gotta have room and you gotta have balls. I'll caution the perverts among you not to dwell too much on that previous statement. Either way you look at this system, you've got 120 microcoulombs of charge available for use. This being said, voltage can be apportioned unequally within the series configuration. Given capacitance equals charge over voltage, an algebraic rearrangement of this expression suggests that voltage equals charge over capacitance. Substituting our given values for capacitor C1 at 30 microfarads and a charge of 120 microcoulombs yields a voltage of 4 volts. Substituting our given values for capacitor 2 at 60 microfarads and a charge of 120 microcoulombs yields a voltage of 2 volts. Voltage across the series combination is 4 plus 2, or 6 volts. This agrees with our earlier observations. These different capacitors hold the same charge at different voltages. It makes sense. Capacitance is a measure of charge storage ability at a given voltage. Capacitance is charge per unit volt. Given the same charge, the smaller capacitor has a higher voltage because it's more full, and the larger capacitor has a smaller voltage because it's less full. Can you dig it? The same amount of charge in each capacitor has filled up the smaller capacitor more, thus it has a higher voltage. Conversely, the same amount of charge has filled up the larger capacitor less, thus it has a lower voltage. This indirect relationship of voltage and capacitance for unequal arrangements of series capacitors can be expressed as a proportionality as follows. Voltage across the capacitor of interest, Vx, is 1 over the capacitor of interest, Cx, divided by the summation of 1 over the capacitors forming the parallel relationship. In this case, 1 over C1 plus 1 over C2. All this times the total applied voltage, in this case 6 volts. Let's use this formula to directly solve for voltage across the known capacitors without having to calculate for charge as previously. Substituting in our given values for C1, C2, and a total voltage, we arrive at 4 volts for V1. An application of Kirchhoff's voltage law demonstrates that V2 is the remaining 6 minus 4, or 2 volts. This relationship works for this simple circuit employing a constant current source, as well as our original more complicated transient analysis of the complete charging process. Consider our Thevenin's equivalent circuit at t equals 0, when we know voltage across the initially uncharged capacitors to be 0 volts. V1 equals 0 volts, as does V2. Current through the series combination of initially uncharged capacitors, 150 milliamperes. Consider an occasion at 1.5 milliseconds, when we know voltage across the series configuration of unequal capacitors to be roughly 8 volts. An application of the indirect proportionality relationship demonstrates that C1, the smaller capacitor, experiences a larger voltage drop of 5.3 volts, and C2, the larger capacitor, experiences the remaining smaller voltage drop of 2.7 volts. Regardless of the unequal distribution of voltage, current through the series combination of capacitors is 73.6 milliamperes. Consider occasion at t equals roughly 3 milliseconds. We know the voltage across the series configuration of unequal capacitors to be 12 volts. An application of the indirect proportionality relationship demonstrates that C1, the smaller capacitor, experiences a larger voltage drop of 8 volts, and C2, the larger capacitor, experiences the remaining smaller voltage drop of 4 volts. Regardless of the unequal distribution of voltage, current through the series combination of capacitors is 36 milliamperes. Finally, at t equals 10.5 milliseconds, the charging process is complete and current flow ceases. Neither capacitor in the series relationship draws any current, and voltage across the total series combination of capacitors is 15.8 volts. An application of the indirect proportionality relationship demonstrates that C1, the smaller capacitor, experiences a larger voltage drop of 10.5 volts, and C2, the larger capacitor, experiences the remaining smaller voltage drop of 5.3 volts. For this series combination of unequal capacitors, you could express voltage across C1 as V1 of t equals 10.5 volts times 1 minus e to the negative t over 2.1 milliseconds. Voltage across C2 as V2 of t equals 5.3 volts times 1 minus e to the negative t over 2.1 milliseconds. Current through C1 as I1 of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds. And current through C2 as I2 of t equals 150 milliamperes times e to the negative t over 2.1 milliseconds. At any time, current through these unequal series elements is the same, however the total voltage is apportioned unequally. Alright, let's move on to a practical application of series and parallel combinations of capacitors with a series of illustrated examples that are hopefully pretty self-explanatory. Let's skip the transient analysis and concern ourselves just with instantaneous values. Consider a box with the label 50 microfarads on the side. We don't know what's inside the box as of yet. All we know it has a total capacitance of 50 microfarads. At t equals whatever, we know that the instantaneous voltage across this 50 microfarad element happens to be 20 volts, and instantaneous current through it is 45 milliamperes. Here's your tasks. Determine the voltage across and the current through the elements in question when the elements inside the box labeled 50 microfarads have the following values. Scenario 1. It is a single 50 microfarad capacitor. Given the above instantaneous data, solve for voltage across the capacitor and current through the capacitor. You'd have to try real hard to screw up scenario 1, although I'm certain it's well within your lazy lab partner's capacity to do so. Scenario 2. It's a parallel combination of two 25 microfarad capacitors. Given the above instantaneous data, solve for the voltage across each capacitor and the current through each capacitor. This should be pretty easy. Scenario 3. It's a series combination of two 100 microfarad capacitors. Given the above instantaneous data, solve for the voltage across each capacitor and the current through each capacitor. This also should be pretty easy. Scenario 4. It's a parallel combination of a 10 microfarad and a 40 microfarad capacitor. Given the above instantaneous data, solve for the voltage across each capacitor and the current through each capacitor. This might take some thought. Scenario 5. It's a series combination of a 60 microfarad and a 300 microfarad capacitor. Given the above instantaneous data, solve for the voltage across each capacitor and the current through each capacitor. This is a little weird, but it's true, and it's well within your capacity to solve. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. Scenario 1. If the element inside the box labeled 50 microfarads really is a single 50 microfarad capacitor, the instantaneous values hold true for the single capacitor. Notably, voltage across it will be 20 volts, and current into it will be 45 milliamperes. Scenario 2. If the elements inside the box labeled 50 microfarad were a parallel combination of two identical 25 microfarad capacitors, the voltage across these capacitors would be the same, and current would divide evenly between them. V1 equals 20 volts, as does V2. I1 equals half of 45 milliamperes, or 22.5 milliamperes, and I2 is the remaining 22.5 milliamperes. Scenario 3. If the elements inside the box labeled 50 microfarads were a series combination of two identical 100 microfarad capacitors, the current through these capacitors would be the same, and the voltage would be apportioned evenly between them. I1 equals 45 milliamperes, as does I2. V1 equals half of 20 volts, or 10 volts, and V2 is the remaining 10 volts. Scenario 4. If the elements inside the box labeled 50 microfarads were a parallel combination of a 10 microfarad and a 40 microfarad capacitor, the voltage across the capacitors would be the same, and current would divide unequally between them. V1 equals 20 volts, as does V2. Application of the direct proportionality equation demonstrates that I1 equals 9 milliamperes, and I2 is the remaining 36 milliamperes. Less current travels into the smaller capacitor, and more current travels into the larger capacitor to achieve the same voltage. It makes sense. Finally, scenario 5. The elements inside the box labeled 50 microfarads were a series combination of a 60 microfarad and a 300 microfarad capacitor. The current through these capacitors would be the same, and voltage would be apportioned unequally between them. I1 equals 45 milliamperes, as does I2. Application of the indirect proportionality equation demonstrates that V1 equals 16.7 volts, and V2 is the remaining 3.3 volts. More voltage appears across the smaller capacitor because it's more full, and less voltage appears across the larger capacitor because it's less full. It makes sense. This highlights why series relationships of capacitors exhibit less total capacitance. When the smallest capacitor in the series relationship is absolutely full of charge, current flow ceases throughout the whole system despite there being remaining capacity in the larger capacitor. It might have seemed odd when I first demonstrated this behavior to you, but hopefully this now makes more sense. Given current doesn't flow through capacitors in the traditional sense, but rather displaces charged particles, the moment any capacitor in a series relationship runs out of room, the whole system runs out of room. In conclusion, we examine the dirty details of series and parallel relationships of capacitors. We learn that the total capacitance figure can be used to determine the general behavior of the charging process. After the general behavior of the total capacitance has been analyzed, one can then use series and parallel properties to determine the behavior of individual elements inside the series or parallel arrangement. Finally, we learn the largest capacitor in a parallel relationship draws the largest amount of current, and the smallest capacitor in a series relationship experiences the largest voltage drop. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.